Take a look at this irregular 3D boundary enclosing a single point charge. If you want to find the total electric flux escaping this shape, you have a problem. The surface bends and warps at random angles, meaning the electric field's strength and direction change constantly. Calculating this via a brute force mathematical integration is virtually impossible. Here, we can apply Gauss's law. Notice what happens to the electric field lines as the boundary morphs into a sphere and then a cube. The total number of lines piercing the surface remains completely constant. The total flux is determined by the charge trapped inside, independent of the boundary's geometry. The equation links the surface integral of the electric field to the total charge trapped inside. The left side captures the flux across the boundary, while the right side scales the enclosed charge by the permittivity of the medium. We have to account for charges sitting completely outside our imaginary boundary. Look at the red field lines from the outside charge. Every single line that enters the sphere on one side must pierce through and exit the other side. The negative inward flux perfectly cancels the positive outward flux, meaning outside charges contribute zero net flux. There is a vital distinction here. While the overall net flux depends exclusively on the trapped inside charges, the specific electric field vector at any localized point on the boundary is a combined result of every charge in the area. Outside charges don't change the net flux, but they certainly push and pull the local electric field. Knowing exactly what is trapped inside a boundary allows us to instantly determine the total flux. We can calculate the physics entirely by avoiding the impossible mathematics. We know the total flux equation is always true, but if we actually want to solve for the exact value of an electric field, we have to isolate it. We can only pull the electric field out of the integral if we design a 3D boundary where the field is constant and exactly parallel or perpendicular to our surface. This diagram shows an infinitely long charged wire wrapped in a cylindrical pillbox. Because the field lines radiate straight out, they graze perfectly parallel across the flat circular caps. That means zero flux passes through the ends. All the flux pierces the curved body exactly at a 90-degree angle, giving us a constant value and allowing us to solve for the electric field. If we move to a solid charged sphere and want to calculate the field inside the material, we draw an internal spherical boundary. Because the charge is distributed throughout the solid, our smaller boundary only traps a specific fractional volume of the total charge. Calculating that fraction gives us the internal electric field. Conductors obey strict rules. Inside the solid metal body of a conductor, the electric field is zero. Because no field exists inside, excess charges are forced to migrate entirely to the outer surfaces. When two plates face each other, this internal zero field rule forces the facing surfaces into equal and opposite charge distributions. Selecting the correct imaginary surface isn't a math trick. It's the fundamental step for finding electric field values in these geometries. Problems become highly spatial in competitive exams. Look at this translucent cube. We have a point charge resting precisely on the flat center of the top face, rather than neatly tucked inside. To solve this, we build virtual mirrors to enclose the charge entirely. By adding a second, identical cube from above, the charge is now trapped in the center of a new, larger boundary. Since the whole system contains the total flux, our original bottom cube receives exactly half of it. We can expand this geometric logic. If a charge sits on an edge, it requires 3 additional cubes to enclose it entirely, meaning our single block sees 1/4 of the total flux. Push that charge to the absolute corner, and you have to stack 7 additional cubes to lock it in the center. Our original cube now captures exactly 1/8 of the flux. Let's test this intuition. For that single corner charge contributing 1/8 of its flux to the cube, what fraction of that flux passes through the 3 red faces touching the charge versus the 3 blue faces opposite it? The electric field lines radiate straight out from the corner origin. That means they graze perfectly flat against those 3 touching faces, contributing zero flux. Therefore, that entire 1/8 share of the flux pierces exclusively through the 3 opposite faces. Dividing by 3 gives us the exact flux per opposite face. Handling boundary charges relies on visualizing the symmetrical blocks necessary to completely trap the charge in the center. Once you see the geometry, the fractions follow. Many problems ask you to calculate the flux from a point charge passing through a flat open disk. Attempting to solve this using standard calculus integrations is a significant time investment during an exam. We can bypass the integration using the solid angle shortcut formula. You draw a line to the center axis and another to the outer edge of the disk to find angle theta. Plugging that angle into this equation provides the total flux passing through that open circle. Let's apply this to a capstone setup seen in a recent JEE Advanced exam. This visual shows a hollow cylinder with a point charge suspended in the center. We need to find the flux escaping through the curved purple wall alone. We approach this by elimination. The total enclosed flux of the entire shape is simply Q over epsilon naught. From that total, we subtract the flux passing through the top cap and the bottom cap. Those end caps are flat disks positioned exactly above and below the charge. We calculate their flux using the solid angle shortcut, subtract both values from the total, and the remaining number is the exact flux piercing the curved sidewall. This summary provides the 4 pillars for solving Gauss's law problems. It covers the core integral, the essential field formulas, the spatial rules for boundary charges, and the solid angle shortcut for non-enclosed surfaces.